hit record. There we go. Okay. Yeah, so I'm going to say that today is going to be the last day of content for you all. So, and the reason why I say that is that I've been working on the Grand Valley Reddit, listening to complaints. Everybody seems pretty stressed out this time of year. So rather than having one more full day of class, I figure we've covered enough. And Friday, let's take the opportunity to do another in-person Zoom session, basically, where I'll create breakout rooms for everybody, and you can all work on your projects, work on whatever you need to finish out the semester. But kind of hopefully to ease into finals week, since I'm sure that's stressful for all of you. So what I'll do is we'll do another Zoom breakout session, basically. And like last week, if it doesn't work that great for all of you, for whatever reason, Zoom was acting wonky last week, feel free to use your Discord channel rooms or however you want to meet virtually. But use it to ask me questions, whatever you need to do to round out the semester. Um, yeah. So we're basically going to wrap up V and V today, and I think that'll probably be good for all of you. Um, so last night I also posted that write-up that I promised was coming, so the teammate assessment. Basically, this will help me grade everybody's contribution to the project. Obviously, I kind of have a feeling for how people have been contributing with respect to like GitHub commits and watching chats and things of that nature, but you all know who's been doing what. And I graded the in-class labs last night, so I also got your earlier feedback, and this is going to be basically have things changed since then kind of a thing. So if you are at the point where you feel like you haven't done enough, if you feel like you're one of those people who maybe didn't contribute enough, keep in mind that software requirements spec is a massive document, basically. It's not due till next Friday, and you can make up some brownie points to your team if you really help contribute there. And unfortunately, this is one of those things where you're going to come back to assessing your coworkers, teammates time and time again in industry. Might as well start getting used to it now. Um, be honest is the best thing that I can say. Being understanding is one thing, but you know, don't be too nice if you don't need to be. That sounds kind of funny. Basically, be supportive, but honest, I guess. What else is going on? So we have that. Those grades are in for the GitLab. Homework 5 is just taking way too long to grade. I've got to revamp how I grade that one next year because there's a lot of things I have to sift through. Um, but if you got a comment from me, like if you're missing 20, 30 points from your assignment, it's probably because either you forgot something or I don't have access to your repository. So just double check the comments that I put in there for you if you're, missing an unexpected amount of points. And I generally gave people a chance to redeem themselves in that case. So just read the feedback. And presentations are Monday, so get ready for that. Again, the information's posted to Blackboard under the term project section of what I'm looking for. Don't worry about posting meeting minutes this week, unless you already have, in which case, good job, but you don't have to have something due by Sunday, basically. And that's about it. Any questions from any of you about the remainder of the semester, anything of that nature? I think we've got at least a handful of people in here. Streamlabs tells me that half the class is in the room, but those numbers are always kind of suspicious to me. Half the time, I think about a third of the people in the room are bots that are just lurking in random Twitch channels. But yeah, if we're good with that, let's move on. So, refresher for all of you. We started talking about the different types of testing last time, right? So we had exhaustive testing, which we said was pretty much a bad idea. Are we splitting presentations into 2 days again? No. So I'll put this in the chat, Corey, just so that everybody catches it. So presentations are all on Monday. We have 2 hours, and at 15 min max, we should be fine. Basically, you are all, like, we don't have a Wednesday class next week. Yep, no problem. I can understand the confusion, but since we have a double class and presentations take 2 days, that should be fine. There's also the possibility that Wednesday somebody's got an exam or something like that too. What time? That is an excellent question because to me, my entire morning is filled with examage. So let me pop out of here because I know it's in the Blackboard. Should be in Blackboard anyway. Term project. It's not in there. I guess I should, let me make this a little bit clearer for you. When is the final exam? 10 a.m. to 11:50. So yeah, there you go. Let me drop this in here right now so that we don't have any confusion. So otherwise, I'm going to get this question again and again and again. So 10 to noon, right there on the homepage for you all. Yes, keep the poll active. And again, for the final presentations, but you already have final presentations in there. Do I? I didn't think I had the time in there, though. I can figure that out after class. Otherwise, it's going to be me dinking around in. I just have the date. I don't have the time. I'll clean that up. We'll clean it up in post. Yep. Okay. So, branch and condition coverage. These were two different types of white box testing, if you recall. So I'm curious if anybody remembers what the difference between these two are. And half the reason I'm asking here is I feel like I didn't necessarily do a great job explaining it, so I want to make sure everybody understands it. We'll do a little bit of Java coverage testing later in a bit too. Anybody remember this? Otherwise, I've got to go on an emoticon or an emoji search here. Hmm. Dancing skeletons. Branch will test if every branch is covered, like separate functions, conditions. Hey, that's in the wrong path. You got to do the down caret. Tested like loop condition or if else conditions. Yeah, pretty much right. So to kind of finesse that, basically branch coverage, if you have different decision constructs, whether it is a loop or a if statement or a switch, any chance that you have different paths of execution, branch coverage checks to make sure that you have a test case that activates that branch, meaning that that code is executed. Condition coverage, like is written there, is checking all of the conditional statements in that decision, right? So if you have an if something, it's checking all possible outcomes of something. you would think that makes sense that, that it would be the same thing, but you can actually have, again, different decisions leading to different branches, or maybe, you don't test all possible conditions, yet you still trigger every branch. So it's basically kind of rounding out testing these statements. Excuse me. And again, we also have multiple condition coverage too. That's where you're throwing in like ands and ors and, basically multiple conditions that we have to test, kind of increasing the complexity of what kind of things we have to cover in there. So good guesses. Um, so that's good. And again, we talked about this last time too, so I'm not going to necessarily spend a lot of time here, but I wanted to refresh you that this is where we are starting with our basis path testing. Finessed. Whoosh. Perfect. Um, But we are basically, again, if you remember from last time, we're taking some program and we are drawing a flow graph of that program. Again, there are automated tools that do this to varying levels of prettiness, I suppose. But in its simplest state, you have nodes, which are the program statements, and you have edges, which are the connectors between them, how you get from one node to another. Right here, node 1 is, again, I equals 1, node 2 is sum equals 0. How you get there is just sequential in the program. But you also might have branching statements where, depending on this condition, you're going to go down one branch or the other branch. And again, conditional coverage would check all values of this condition here. Let me get my little pointer. This condition here, whereas branch coverage checks to make sure that all paths of execution are performed, right? So this is about where we left off last time. We were talking about, oops, sorry about that. Hey, look at all these notes I have to talk about. We kind of left off talking about cyclomatic complexity. And Google, you are not my friend today. That's where you're trying to figure out basically how many paths of execution there are, right? That's how complex your program is. And we had three functions that we looked at, right? We had the enclosed regions where you basically count effectively how many loops there are, right? How many enclosed regions, it's just you have nodes and edges like forming a little bubble in your program. We also counted the number of edges and the number of nodes, and we just applied a mathematical formula to that. So the number of edges minus the number of nodes plus 2. The other one, we talked about predicate nodes. So this is where you have a node with 2 or more edges coming out of it, which is a branching statement basically, right? You have 2 or more possible paths out of it, meaning that you are now creating complexity in your program. So it kind of makes sense to have a formula based around that. And you might have the question, which one of these do you pick? I would say it kind of depends on how complicated your program is and how hard it is to analyze. You're ideally going to get a similar answer or the same answer out of all of these. The more complicated your program gets, you might start seeing some variation in them. But I would honestly pick whichever equation is going to be easiest for you to apply to it, kind of at its simplest state. All right, so here's our program again with our nifty little flow graph. So again, step 1 was that we drew it, meaning we understand the code enough to draw a flow graph. Then we calculate the cyclomatic complexity. I think this is actually where we left off, right? So the enclosed region method, how many enclosed regions do we have? 1, right? That is an enclosed region right here because we have this little bubble, this little loop construct. So 1 plus 1 equals 2. I'm going to assume you can all do addition, and if you struggle with that, there's the calculator app team, which is working feverishly to help you out. We have the edge note method, where it's the number of edges minus the number of nodes plus 2. In this case, again, 6 edges, 6 nodes plus 2. Cyclomatic complexity of 2. Use the predicate node method. How many predicate nodes do we have? 1. 1 plus 1 is 2. So in this case, in all examples, we have a cyclomatic complexity of 2, meaning that we have to write enough test cases to execute 2 branches of code, right, or 2 execution paths. So that's basically, again, what we're getting out of cyclomatic complexity here. So with that, you have to now figure out what paths are going to be representative of that cyclomatic complexity. So we're going to call this an independent path, right? And again, this is your visual trace where this is a unique flow through your program, okay? And that should match your cyclomatic complexity. So again, for this example that I showed you already, it's really easy, right? It's 1, 2, 3, 6, 1, 2, 3, 4, 5, 3, 6. We have two independent paths of execution, right? So from there to there to there to there, or loop around and then go down. What is an independent path? What this means is that you have to have at least one edge that was never executed before, right? So that's going to make it unique or independent. Excuse me. So you might be looking at this and say, well, 1, 2, 3 is executed for both paths. You're like, yeah, that's true. However, for the first one, 1, 2, 3, 6, we'll call that our first independent path. There's nothing to check, right? So a set of 1 is unique. But when you add in the second path, 1 to 2, 2 to 3, 3 to 6, that already exists. But the new little extra bit is 3 to 4, 4 to 5, 5 back to 3, and then 6. So we have this unique path of execution. And again, intuitively, this makes sense, right? We have similarities, but there's still enough difference that it is a unique path of execution. You can take this kind of general written out formula, and you could honestly apply this to an automated algorithm, right? So if you create let me walk through this kind of as a mental exercise here. So let's say that we have a set, right? Which you could take to be, there's Java, Python, set functions, dictionaries, whatever you're going to call them. Basically, you're only going to have one unique entry, or every entry has to be unique, basically, is a better way to say that. If I add, we could call this like an array or a JSON object or something like that. Effectively, it's a linked list. You pop in 1 to 2, 2 to 3, 3 to 6, that's one entry. 1, 2, 3, 4, 5, 3, 6, that's a second entry. It is unique in that sense. You could apply this to an automated algorithm where you just keep traversing your flow graph. If I get 1, 2, 3, 6, okay, the next path that I run is 1, 2, 3, 4, 5, 3, 6. Add that to this object. Are they different? Yes. Now I have two paths of execution. Try another one. Is this unique? No. I might be done with checking if I have any more unique paths. What I'm kind of maybe poorly explaining, or at least poorly trying to conceptualize for you here, is that this doesn't have to be done by hand. This can be automated. And you can actually use pretty simple tools to get that done too, which is handy, again, because your programs are going to be pretty darn complicated, right? They're not going to be sum the numbers up. They're going to be, here's my massive Android application with a ton of separate screens and moving parts, calls to a cloud function, calls to an SQLite database, and we have hundreds to thousands of paths of possible execution. So making this easier on ourselves is always going to be a good thing. But that is figuring out the paths, right? Should match cyclomatic complexity. The last step is to figure out which test cases you're going to create to exercise this set of paths, right? So what are the input conditions that trigger every single path of execution? And in this case, again, it's pretty straightforward because it's a very simple program, but we're testing the inputs. What are the inputs? Well, it's this value of n, right? So n is less than or equal to 0. It's going to go down 1, 2, 3, 6, right? Because we're expecting an output of 0 because we never trigger our loop value. So if 0 comes in, right, I is initialized to 1, sum is 0, I is less than or equal to n. This is 1 is less than or equal to 0. Skip the loop, return sum, which is 0, right? Inputs to outputs. If you input anything greater than or equal to 1, you exercise that other branch, meaning that loop gets triggered. And we don't necessarily know exactly what that value is, but we know what it will be in relation to n, right? Because it will be the sum. So the sum of 1 to n is going to be whatever you put in. And now the question then would be, let's say we put in n is greater than or equal to 1, and maybe we're using a language where it's not as nice for you. What happens if you get up there in you start hitting that boundary for integer, the boundary for how much an integer can hold, right? You hit that 2 to the 32 upper value. Maybe now we have a hidden third path of execution where we go 1 to 2, 2 to 3, 3 to 4, 4 to 5. We do that 100 times, and then we die because we can't hold any more values in our program segfaults. So that might be like a latent hidden path of execution that we don't necessarily catch. And in that case, you would need a third test case to trigger that. Okay, so this would be a lot easier if we were in person or doing this on a Zoom or something like that, but I'll kind of ask the chat as we go. So here's a straight up factorial function, right? So we have something pretty simple here where it is not recursive, so you don't have to do what my undergrad professor said and bang your head against a concrete wall until you understand the concept of recursion. We're just going to use a while loop here. So we have some variable declarations. If n is less than or equal to 0, or sorry, if n is less than 0, factorial is 0. Otherwise, perform your standard factorial calculation and then return the whatever you calculated, right? So you have your sanity check state, your function, return the output value. And what we're going to be doing here is let's actually, step through this process of coverage. All right, so first things first, we have a flow graph that we have to draw, right? So what do we have here? The line numbers that I've got would correspond basically, directly to what you would see in an editor. So even the function declaration, the variable declarations, they get their own line number. So we're not starting at 1 over here, we're starting at 3. Right, so 3, if n is less than 0, go to 4, and then go to 13. Right, so 3 to 4 to 13 is one path of execution, which means we trigger, or we check this if statement. It's true, therefore we say factorial is 0, and then we skip the else statement and go right to the return, right? So path 1 is here, 3 to 4 to 13. Path 2, we start with 3, right? So we check our if statement. It's false, so we go to the else case, right? Which is 6. I equals 1, factorial equals 1. So I equals 1, using my mouse pad here. I equals 1, factorial equals 1. Go to the second decision statement, which is this loop, right? So basically we have 2 branching possibilities in this program. A little bit more complicated, but not by much in the grand scheme of things. So 8, I is less than or equal to n. Is I less than or equal to n when I is 1 in fact is 1? Yeah, absolutely, right? So it's true. So then we go into 9, 9 goes to 10, we go back to 8, we loop around until this value is no longer true, and then we bail out. Nothing else happens except we go to the return statement, right? So if we were to draw this out, like on a whiteboard or chalkboard, if we want to be fancy, which is weird to say that that's fancy now, we would kind of iteratively draw this out, right? And we can kind of see how we would build up a flow graph. You just kind of go line by line, add in edges, add in nodes, connect the edges to those nodes however they're represented. Right here we have our conditional. Conditionals are going to be an if statement or a loop statement or a switch, anything that branches. You just kind of draw it out. And one thing that will be helpful for all of you, I'm not having you do this in class or anything like that, but if you do this on, like a drawing program, like Draw IO or Visio or OmniGraffle, whatever your drawing program of choice is, you can move things around a little bit easier when you screw up. So like if I didn't lay this out nicely, I'd have to erase half of it and redraw it, right? If we're doing it by hand. But if you're doing it on the computer or a tablet or your phone or whatever, you can move things around nicely. And if you get one of those nifty programs where lines snap to other things, you don't have to move lines around. They just kind of automatically draw themselves. It's kind of one of those little handy things you can do if you're having to draw out flow graphs. But straight up, factorial makes sense, right? Any questions so far? I'm spending a lot of time on this, but I want to make sure everybody kind of gets the concept. Again, what you can do if this does not make sense, I've got a example for my grad class for tonight here. So this is in Python. Just what are the line numbers in your code editor, right? So you don't necessarily have to make it pretty. Like the start of my program here could be line 19. So my node starts at 19. Sorry, I forgot my question was, nope, did it make sense or does it not make sense? If we're all good, I'll just continue on. Feel free to ask questions if you're lost, though. All right, so we are here, right? We have our graph. Next step was calculate the complexity. Hey, Fredericks, it's Tove. Hey, Tove, how's it going? Been a hot year. Dropping in for the last software engineering class. Awesome. Thank you. Okay. I guess let me throw this out there for you all to kind of mull over. What I will be doing on Friday is asking you how you like the Twitch class versus doing it in something like Zoom or Blackboard, because I'm trying to figure out if I want to do it again next semester. Because we've got this class again and computer graphics and waffling if I do it on Twitch or not. So if you got any thoughts on that, drop it in the chat and I'll kind of peruse them as we go. I like Twitch. I like the interactivity of Blackboard/Zoom. I can see the pluses and minuses to both, but just let me know what you think. Okay, so enclosed regions. This was the first way we can do cyclomatic complexity, right? So again, we're just looking at how many areas are bounded. I like Twitch better than most Zooms. Okay, that's good to know. So the thing that I love about doing it on Twitch is that I have horrible short-term memory, it seems. And if I start talking or doing something, I forget very easily. And I can just yank things down off of Twitch when I forget to record. I would say I've probably forgotten to record about 75% of the lectures, honestly. So it makes it easy for me, which is nice for you all. Okay, I'll keep that in mind. Thank you. So here we have two enclosed regions, right? Again, makes sense. We have two branching statements. These kind of lead to these two little bubbles in our program graph. So equation, again, simple. How many enclosed regions do you have? +1. Here we have a cyclomatic complexity of 3. And again, what does that actually mean? That's how many paths of execution we have, right? So we have 1 here, bop, 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 bop. 1 here, 3 to 6, do, 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 do. Then we have our third one down this side, around this loop, back to 13. The one thing that I didn't really mention too is that the number of looping statements doesn't really matter from this perspective. You're just looking to go down a path. We don't have any constraints on here where you go through this sequence 50 times versus 500 times. In this particular view, this loop is all going to be the same. So it's not like 8, 9, 10, 8, 9, 10, 8, 9, 10 versus 8, 9, 10, and then bail. We're going to consider it the same. All right. So then we have the edge node version. So that's how many edges to how many nodes we have. So again, number of edges minus number of nodes plus 2. In this case, we have 9 edges. We have 8 nodes. Add 2. Cyclomatic complexity of 3. So still the same there. Third one, predicate node. How many predicate nodes do we have? Well, if we remember like 5 minutes ago, when again we talked about predicate nodes, that's where you have a branch condition, right? Could be branch of 2, could be a branch of 100. Doesn't matter. We have 2 of them here, right? So there's our first predicate node is 3. Second predicate node is 8. Again, that was your if statement at the top, your while loop at the bottom. 2 plus 1 is 3. All of our arguments or all of our functions here agree. Cyclomatic complexity of 3. We have 3 paths to test for. Okay. Now, what does that mean for testing then? I forgot to actually add that into the slide, I think. But how do we test this out now, right? How do we trigger these different paths of execution? Well, first time is actually pretty straightforward, right? You feed in -1, and then we get a factorial of 0, or maybe you want to throw a different error condition to tell the user, hey, idiot, don't feed me an invalid value here. Feel free to put that into your programs to mess with your coworkers. But so one path of execution would be our invalid value, which is a good state to check. So test case n is -1. Second test case, what we're going to do is figure out how we can trigger this while loop in multiple ways, right? So it's a very simple conditional. So we have to have I is less than or equal to n, and I is greater than n. So in this case, I equals 1, we could have a test case of n is 2. So that would trigger going into the loop. Or we could have n equals 0. It would not trigger this first one, and it would not trigger the second one. So then we get our third path of execution. So kind of what I'm trying to get across to you all here is that we have basically, we're basically doing conditional and branch coverage with these very simple examples. The more complicated they get, the more you actually have to focus on what test cases are doing what, right? If we had multiple conditionals, if we had very complicated if statements or branching statements, the number of test cases is going to increase. But what hopefully you're seeing is that by systematically testing and figuring out some of these very simplistic metrics, you can kind of get a feel for how many test cases you need to write to accurately white box test this little form or this little function here. All right, so we've got some static techniques, a little bit of debugging to talk about, some coverage testing, and then that's pretty much it for today. So let me pop up something. So here we are actually going to step away from the code a little bit, and we're actually going to talk about your artifacts, because we haven't really talked about checking those. We've always kind of assumed your requirements are perfect. But as you're all seeing with your requirement specs that you're developing, you are basically, you're developing these by hand, and there's always the possibility you have errors there, right? I gave you all feedback that, hey, these requirements are good, these ones are crap, you need to fix them, which is not what I said in your reviews, but it's more of a generic comment there. But how do you fix that? You don't have necessarily an automated test that you can run through, right? You have to actually read things and understand them. And generally, the best way to do that is either as an impartial third party, again, like you're somebody in the quality department checking over requirements or these artifacts, or you walk through them with your team in like a meeting-based setting, right? So let's read through every requirement, talk about every single one to make sure that everything is clear, concise, and does what we're saying it should. So we're taking these requirement specs and making sure they are the ground truth for your program. Because if they're suspicious, then your program's going to be suspicious, right? Because we are programming to that spec, we are testing to that spec. If the spec is bad, garbage in, garbage out is kind of the standard statement there. So what is a review? Well, we could do a walkthrough where we prepare everybody, read the spec ahead of time, come to the meeting with questions, with comments, with marked up documentation, and let's analyze it, right? There's a lot of analysis processes that are out there, but at its core, you're just kind of reading through them and making sure they make sense. Maybe acting things out, maybe role-playing a little bit in a meeting type of setting where somebody pretends they're the customer. You pretend you're the engineer trying to sell them on all of these requirements. Let's talk about requirement 5. This is implementing a login button on our home screen that will automatically check if the case is correct, if the correct number of special characters are in there, so on and so forth. But you can actually act it out. So that's one way to do it. It's kind of informal, like a walkthrough. You also have formalized ones, so an actual inspection where you may have multiple steps. You could consider these steps to be like meetings where we deliver this requirements back to everybody. Here's what we're planning on doing. read through it, check it out, give people a checklist to go through. You know, you're doing requirements 1 through 5, you're doing 6 through 10. Here are all of the points that you need to consider when reading these requirements. You can formally inspect them and follow your process. Then do a reworking stage, right? This is going to be like any software process we've talked about this year, right? It will be cyclical, meaning that you have a chance to go back and fix things if you F up or if you screw up. So basically, you have this kind of little bubble of a software process, right? Start high, read through it. If you have to fix things, loop back around and just keep going until you're happy with your final product. We can also desk check them too. So I, the engineer, come up with, here's 100 requirements for this project. Give it to somebody else, have them read through it and see what they think. There's multiple ways that you can do a static analysis on your artifacts, and you have to pick the right one for your particular environment. But the thing is that you have to do this. Otherwise, you never check this ground truth specification, right? We have to make sure that everything is right and correct. Otherwise, you may have a bad product at the end of the day. The other side of things too, which gets into the more advanced side of software engineering and is not always done in industry. It's recommended in academia and research, but you can do correctness proofs where you model your requirements as like a formal logic. Maybe you add temporal constructs, meaning this particular thing happens at X time, which leads to this requirement being triggered, and basically take your whatever artifact you're looking at it and you turn it into some kind of a formal automata, and then you apply a bunch of crazy model checking features to it. Hasn't really gotten entrenched in industry unless if you're a very forward-thinking one. But what you can get out of that is a very nice formal mathematical proof that, yes, your requirements make sense and they're doing what they should be. I'm going to gloss over that here, but it's one of those things that are out there for you. Okay, so we are now basically at the end here. So now we have checked our requirements, we've run our tests, we've done everything we need to do, and then we discover a problem. Okay, go get some water then. I can't. Okay, I'll get it after class, okay? Hi. Hi. Almost done. Honey, you gotta go, okay? Go ask Mom. Here. I've been bombed, okay. Twitch bombed or raided, or what's the term? Okay, thank you. All right. So, but she just wants water. No, she got water. It's okay. Love boundaries. Okay, so let's say a test case failed, right? What do we do in that case? We have to debug, right? So whichever test case you have applied, you've detected a failure, you know it's going to be because of some inputs, because of some or because of some paths of execution. Hi, yep, it's hilarious. Let's be in Dad's class. So what we're doing here is that you're trying to zone in on what is the actual cause of failure, right? And whether you debug with trace debugging statements, whether you run a formal debugger, watch variables, set breakpoints, whatever you need to do. I am impressed it took all semester to get to this point, where it's hilarious to get into Dad's meeting. Basically, you just try to apply an iterative process to find the problem, okay? Try to zone in on what are the actual inputs that trigger this failure. And again, it can be a failure in your test cases, it can be a failure in requirements, it could be a failure of implementation. You have to basically rigorously and iteratively try to find the root of the problem. So how do we do this? Some of you have kind of zoned in on the rubber duck debugging technique, which is wonderful. Get yourself a little friend, right? I don't have a rubber duck handy. I've got Gucci Kopi here from Bob's Burgers. Put it on your desk, explain your problem to it. It will not judge you. It will not talk back. It'll just sit there and passively listen. Hey, I screwed up my loop statement, and you just kind of watch it there. But you'll find that talking out your problems 9 times out of 10 will point you in the right direction. If you need, bring in another person, describe the problem to them, have them look over your shoulder while you code, share your repository with them. Basically, use whatever techniques that you are comfortable with and aware of to try and find the problem, right? And that could be as simple as talking it out with your rubber duck or your favorite tchotchke, whatever you've got. You can do your other standard debugging techniques. Do some brute force debugging. Add a print statement to every line. Print out a variable type. Print, I got here 2, I got here 3. Set a breakpoint in your debugger. A little red dot in your IDE. You hit play with debugging. Program runs until that point. Then you start watching variables as you step through the program. Maybe you're stepping, and you never get into that if statement that you thought you were going to get into. Basically, use all of the tools that you have in your tool belt to find the root of the problem. And again, sometimes it's the simplest things of just talking it out. You might not be expecting an answer, but verbalizing it will take that problem and kind of crystallize it in your mind there. So, let's see. I've actually been talking about this. So brute force is kind of effectively what I've been talking about with like trace debugging, using debuggers, things of that nature. You can also do something called backtracking, where you localize the root of the problem, right? You know the inputs and outputs of the test case, you know what fails at this particular line. Work backwards. So go back in time. Okay, what's the variable here? How did we get into this function? Basically start localize and kind of work your way backwards and see what are the conditions that led to this problem. Could be a simple fix. Could be a problem at the requirements level, right? It just kind of depends. All right, so one thing that I wanted to get to is look at some of this coverage aspect in Java as well. Debugging, I'm hoping that you all will pick up over time, right? It's going to be a learning process, whether you're getting comfortable with PDB, whether you're using Java's built-in debuggers in which Eclipse or IntelliJ, whether you're using C, you're using command line debugging. Basically, you have to figure out the best way for you to debug, right? And there are a lot of ways to handle that out there. But it's one of the more difficult things to do, honestly, figuring out how to debug and when to debug. But I'm going to leave you with V&V for that. I want to show you this code coverage example from our Travis CI tutorial before we kind of wrap for today. And again, while I'm going through this class Friday, we'll do it on Zoom so that we can have another collaboration session. But this is going to step back to our Travis CI tutorial here. So you all did the build tag, right? So we did the unit testing. Let's look at code coverage now. So what I want to do is I'm actually going to take the easy route, and I'm just going to fork this particular project here rather than create my own coverage statements. This person already added it. All right, and hey, we have GitHub dark mode now, which is delightful. But I've got this tutorial now forked into my repository. And what I'm going to do is I'm going to enable it in Travis. I'm kind of doing this again, darker than my soul. Yeah, that's how I describe my coffee. Black like my heart. All right, so I need to go to settings. Let's activate this. Black coffee is best coffee. So it's Travis. Okay, approve. Alrighty, so we've got that. And in the tutorial, basically they said just update the README and that'll trigger a build, which I absolutely agree. That will happen. So I am now E. Fredericks, copy paste, up, up. And what this is going to do, so I'm just updating the README here with my name just to update those tags, triggering a build. But what is interesting here for all of you, and why do you care about this? So this is, again, that unit testing lab that you all basically did before, except now we're adding in code coverage, okay? And how do we get this little code coverage tag? Well, in travis.yml, we have an after success. Let me zoom in on this a bit so you can all see. It's going to do something after we are happy with our build, right? So if your build failed, you're never going to get to this step. But if things are successful, reach out to Codecov.io and trigger a code coverage check on this project, right? So what is Codecov.io? Well, it's another third-party API that basically checks your Git repo to see, hey, what does your code coverage look like? And it's pretty straightforward in Travis. You just bash, and then we're going to call code coverage, call their API, and it's pretty easy. Didn't have to sign up for it. It's just kind of there. There is more to it than that as well. So in, is it pom.xml? So this is basically part of the build that this person set up, and why I didn't want to do it myself, because it already exists. But he adds in a plugin. So this is your Maven build, the pom.xml. But let's add in Jacoco, which is a code coverage plugin. And codecov.io is basically going to look and see, okay, let's use Jacoco to calculate out the coverage for this project. So that's there. Travis.yml is saying call codecov.io. The source code looks identical, no changes here. Here's your simple calculator. Here's your test cases. Again, nothing crazy going on in this source code. But we now have a Travis build running, right? And we forgot about it because we started talking about other things. But build passed, life is good, wonderful. Let's refresh our home page here, or our repo. So we should refresh and eventually it should come in. There we go, build passing. Code coverage 71%. What does that mean? You zoom in. Code coverage 71%. Expected for this example, by the way. It's not like, oh my god, I can't believe only 71% is passing. Well, we can click this. How cool is that? We can click things. All right, we have now this codecov.io page where it's looking at our Git repo. And we have a sunburst, which not necessarily going to talk about here because I don't necessarily understand how this graph is supposed to be read. But down here at the bottom, it's telling us our complexity and our coverage, right? So the value that we get out is that about 71% of our program is covered. Well, what does that mean to me, the programmer? Got some colors here. I've got some lines missed, lines hit, complexity. These values that we talked about are basically, existing. Pardon? This was not there yesterday. Hey, hey. I wonder if something in the GitHub universe update broke this. What? Uh-huh. Okay, cool. Well, what this should be showing is that browse report. Can we do that? Are you kidding me with this? Of course. Live builds. This is what happens. Pardon. This is how you all felt during the Travis lab, right? I literally did this last night and it was fine. So, all right. Okay, so let me go back to my Git repo here. Maybe that'll help. And then you can all head out. Of course, this is happening in class. Let me show you what's going on here. What you should be seeing in that report is that all of these cases are covered. This case is not covered because we never actually instantiate and run our program with our unit tests. So code coverage is checking, do all of your tests run every single line of code that you have? And we do not get that because this void main is never triggered basically by the test cases. So that's all it was. I'm gonna have to look into this for the afternoon class now because that's hilarious. All right, that is it for today. Sorry for holding you over an extra minute, but hey, live demos are always fun, right? I will see you all on Friday on Zoom. We be zooming. And then don't forget Monday will be your final presentations. So, bye everybody. Hope you have a wonderful day. Tovo, thanks for dropping by. Always nice to see old friends come in. And yeah, have a wonderful day, everybody.